In this video, I wanted to cover a little bit more on units. Over the years, I think that in my mind, units is sort of inherently, I would say, easy. I guess is the way I would phrase it. It's easy in my mind, but that's only because I've worked at it. You know, I've been an engineer for a long time, and it gets to be the point to a point where things are pretty much automatic, and you don't have to think about them all that much. And so whenever I'm talking with students that are new to engineering or people that are wanting to become an engineer, I think I fall into the trap of just thinking you're going to know how to do it, okay? And sometimes it takes a little more thought on exactly how to work your way through this in an efficient way. I have a saying, nothing is obvious until it becomes obvious. And I think you'll get to the point where unit conversions and how to solve unit problems are obvious. But, let's talk about all the steps in a little more detail. All right, so I'm going to start with an analogy. All right, so most of you, I assume, know how to drive. And there's a point in time where you were learning how to drive. All right, so let's do a little thought experiment. It's a little more than a thought experiment. You need to act this out. So let's pretend like we're going to drive, and we're going to put our hand on top of the steering wheel. Okay, so we're driving along. Now I want you to think about how would you manipulate the top of the steering wheel. I'm not talking about turn signals or anything. I just want to do a lane change and concentrate on what happens to the steering wheel. All right, so go ahead and do that. Make the lane change. Okay, think about how that happened, and maybe pause the video and then come back. All right, so how did you make your lane change? Okay, so I think what a lot of people will do is they'll say, okay, I'm going to change lanes. I would veer over a little bit, and then I would come back. All right, is that what you did? Well, if you did that, congratulations, you made a turn. You didn't do a lane change, okay? Because if you think about it, or if you observe yourself driving, I've had some students argue with me about this, but if you want to make a turn, you start straight, you turn, and you correct back to where you're going straight. If you're going to do a lane change, you actually have to turn a little bit and then turn all the way back the other way to straighten back out and come straight again. Okay, you're essentially making two turns with the lane change. Okay, so what's the point of that? Well, the point of that is everybody knows how to drive, all right? You know how to do a lane change. But if you try to explain it to someone by just manipulating the top of the steering wheel, you possibly explain it to them incorrectly, all right? So that's what I think happens when we talk about units. It's such an automatic thing that sometimes it's not obvious on how the best way to teach it would be. So I've been thinking about that, and I wanted to talk about units in a little more detail and the importance of units and why we're slowing down a little bit. I know a lot of you probably feel like this is already automatic for you, but we're slowing down because I want to make sure we get this right, and nothing's obvious until it's obvious. So if this is not obvious to you yet, it doesn't mean you're not cut out for engineering. It just means it hasn't clicked for you, all right? You had to learn to drive at some point. Same thing with handling some of these basics from engineering. Okay, so the next thing I want to do is go and share my iPad screen and talk about a little more systematic approach of how we're going to look at units. Okay, so first of all, units are a big deal in engineering. I don't know if you've heard this cautionary tale before. It's one of the most famous cautionary tales out there in terms of units. But there was a mission, a Mars Climate Orbiter mission that I think this was in 1999. I have to look it up to be sure. But it failed, all right? It turned out the flight dynamics didn't work, and the thing just burned up, and I think it burned up in Mars' atmosphere. And when they looked at the cause of the reason the mission failed, is because there's a collaboration between US engineers and European engineers. And US engineers were doing some calculations in the English system because we grew up thinking about that. English system's natural for us. And then in the communication with some of the European engineers, they were expecting data in an SI system. So really, it was just a unit conversion problem caused this. It was embarrassing, but it happens. All right, so it's important to know these things. And then later on, I'm going to point down here. I'll do that here. Later on, we're going to talk about MATLAB. And MATLAB is a modern tool. And I think if you look into it, MATLAB, this is something new for me. I'm adding it in 1301. But MATLAB can help you keep track of units and make you be more systematic about how you think about units. Okay? All right, so the next thing I want to talk about in this brief lecture on units is, as I'm thinking about the analogy between driving, changing lanes, how do we do this exactly? What's going on when we just naturally know what to do with units, and what are people missing if they don't naturally know how to deal with units? I think what's going on is there's actually two things that you have to be able to do. One is you have to look at the governing equations, okay? And because I'm an experienced engineer, I might overlook your lack of knowledge about certain governing equations. It doesn't mean you're not going to be a good engineer. It just means you don't know that yet. Nothing's obvious until it's obvious, okay? So there's that step. And then there's the actual process of converting units, okay? And so we've talked about unit systems, English versus SI, for example. We've talked about base and derived units, and there's rules for making these conversions. If you go through this systematically, you can get good at doing unit conversions, okay? But I think some of the confusion early on is a result of the confusion or being mixed up with the governing equations aspect of some of these problems that we'd like for you to solve. Okay, so I want you to focus on some problems here where we're looking at governing equations separated from the actual unit conversions, and we're going to use MATLAB to help delineate that separation. Okay. The next thing I want to talk about is sort of some base knowledge. Remember, we talked about Bloom's taxonomy and the need for this pyramid to be able to rise up from some of the base elements of the pyramid up to where you can do more analytical and creative things. So I was thinking, how about, me personally, I write down what I know about unit conversions that are just in my head, okay? So I started writing those down, and I always use 2.54 centimeters is equal to 1 inch, okay? And I think the reason that was taught to me is because that's an exact conversion, okay? So you might think, well, 1 meter is about 3.3 feet. Well, it's about that. And if you can just remember this one easy conversion, this is an exact conversion about round off, okay? The other interesting conversion to me is the metric conversion between a volume and a liter. Okay, so this is one of the reasons for the advantages for the metric system is some of these tricks work really well, and English system doesn't always have them. Okay, so I always think of 1 cc, 1 cubic centimeter, is the same thing as 1 milliliter. Okay, and that gives me a connection between the length dimension and the liquid volume. Well, not always liquid, but the volume dimension in liters. Okay, so I know that one. And then this one is not exact, all right, but it's the rule of thumb that I remember, 2.2 pounds and 1 kilogram. I have that one in my head. The other thing that I try to keep in mind, and we've talked about mass versus weight with a couple of videos. 1 pound mass on Earth turns into 1 pound force using the standard gravity. weight is equal to mg. Right? So I know that substitution or conversion, if you will, if we're on Earth, and we're usually on Earth when we do these problems. Okay, of course, I also have in my head gravitational constants for both the SI system and the English system. Okay, and then, I'm telling you a bit of a lie. I don't remember these. Okay, so it'd be nice for you to remember those on the exam, but generally, if I was going to ask the more detailed conversion, I'd probably put that on the exam. Same thing with a slug. I know that, one slug is correlated to the gravitational constant of the Earth, and so that one's an easy one for me to remember. 32.2, that's the gravitational constant of the Earth. That's no coincidence. That's how the slug is defined in terms of pound mass. All right, now I'm listing some things that for US students will be obvious, okay? I think you already know these things, but if you're not a US student, if you're an international or from Europe, you spend a lot of time in the US when you're learning systems and units, you may have to do some work on this, all right? So I expect you to know these typical conversions, okay, in the US system. One of the things I wrote down here, because I've done a lot of work with the Navy, 1 nautical mile is less than a mile. I don't actually know the exact conversion. I just know it's not the same thing. And so that's an important thing to realize if you work in that particular area. All right. The next thing that is in my head that I thought of when I was writing all these down is that when I drive a car, I've driven a car over in Europe, and typically speed limit signs are posted in kilometers per hour. And you look down at your dashboard, you can tell 100 kilometers per hour is the same thing as 62 miles per hour. Right? So you can drop the per hour part, and you know that 100 kilometers is 62 miles. That's another way of thinking of it. Okay, the other thing that I do is I know all the SI prefixes, well, maybe not every one of them. The ones that are way up there are really, really small. I don't necessarily know, but I know nano through tera, beta. Okay, so be sure you know those. I probably wouldn't ask you to know this on an exam, but I think just functioning in the United States, it's nice to know these conversions as well. Okay, so what I want to do next is do an example problem. We're going to do this problem, and then we're going to convert it into MATLAB, a MATLAB approach, and I'll talk about the advantages of the MATLAB approach. We're going to do a few of these for this week's work. Okay, so I'm calling this problem, will it float? All right, so we're considering a sphere with density 0.025 pound mass per inch cubed. It's known that the density of water is 1,000 kilograms per meter cubed. I actually remember that one as well, so that can go on my list. So the question is, will the sphere float in water? All right. So you notice this requires some knowledge of a governing equation. All right. It may not be obvious what that governing equation is, and in fact, we haven't talked about buoyant forces. All right. So it turns out the force working on an object, in a liquid, is proportional to the displacement of the volume of that object. All right. So you might think, well, I've never heard of that. Okay, but sort of the intuition that engineers have is if it's a sphere, there's no hollowed out part that's going to just let you reduce sort of the density of the object in terms of weight per volume. And so as an engineer, an experienced engineer, I quickly jumped to the conclusion that what we're asking for is to compare the density. I should put different subscripts. So the density of the object, okay, so I'm going to call that 0, and the density of the water. All right, so the idea is if the object is more dense than water, it's going to sink. If it's less dense than the water, it's going to float. All right, so I simplified in my mind the governing equations, and if you haven't seen that kind of thing before, that makes this problem hard. And you're not really having trouble with units, you're having trouble with the governing equation. Okay? So think about that as we work these problems. What is the governing equation that we're talking about? And then we'll go straight to the unit conversions. Right? So, it would have been a lot more, it would have been straightforward if I had said convert rho naught into kilograms per meter cubed. All right? So had that been the case, it would have removed that governing equation complicating factor out of the mix, right? But we're trying to teach you to think as an engineer, and so we want to pull in these governing equations to develop your skills in that area. So hopefully that makes sense. Okay, so let me start from scratch. All right, I have this written out. I meant to delete it. Right? So. Right, so what we're going to do here is we're going to now do unit conversions. This is purely unit conversions, and we don't have to worry about the governing equation because what we're simply doing is we're trying to convert rho naught, 0.025 pound mass per inch cubed. We're trying to convert that to kilograms per meter cubed. All right? So I'm thinking to myself, what do I multiply it by in terms of conversion factor to move me in the right direction? Okay, so one of the first things you could look at is let's convert inches into the metric system. Okay, so if I'm converting inches into the metric system, right, I would need to use conversion factors from my list, right? So on an exam, I might say, use only the conversion factors from this list to make these conversions so I can see that you know the thought process. Okay, so what we had on our list was the link between length in the English system and length in the metric system was that there were in 1 inch. Okay, so I put the inch on top because I know I needed to cancel with the denominator. Okay, in 1 inch, there's 2.54 centimeters. Okay, but I've got this cube here. All right, so I need cubic inches to cancel, and so I cube the whole factor. All right, so that means this 2.54 gets cubed and this centimeter gets cubed. Right, so I don't write that down because in my head I just know that. All right, you could just break that down and make another step. All right, so I now have inches cubed canceling, right? These cancel, and what I have is pound mass per centimeter cubed. So I need to get centimeters into meters, all right? So I know that there's 100 centimeters in 1 meter, but because of this cubing, this is cubed. So I need to get rid of the cube, right? Or cancel the cube. So this part needs a cube as well, right? 100 cubed, right? So now I've got this centimeters cubed canceling, and I'm left with meters cubed on the bottom in the denominator. All right, so that's looking good. Now I just need to convert pound mass to kilograms, and so I look at my table. 2.2 pound mass is 1 kilogram. All right, so I check. I have meters cubed on the bottom, pound mass cancels, centimeters cancel, inches cancel. I'm left with kilograms per meter cubed. All right, and so when I plug this in, I get this as the answer. And back to the governing equation. Is this less than the density of water? Yes, it is. So that means this sphere would float. Okay, so those are the steps involved. Notice how I separated those things out. And I really want you to be able to automatically do unit conversions. And then hopefully you will recognize enough of the governing equation kind of problems where it won't complicate your life, where you won't be able to answer exam questions, right? So we'll always, or we'll try to focus on breaking that into two different components, the governing equations and the pure unit conversions. All right, so what I'm going to do next is I'm going to rework this problem in MATLAB. And MATLAB forces me to encode this in MATLAB. It forces me to think of unit conversions. All right, so we'll do some more examples of that. So hang on, I'm going to switch over to MATLAB and we'll continue from there. Okay. Right, so changing the screen. MATLAB live editor. Okay. So in this live editor, I'm going to rework this problem using MATLAB. And the reason I want to show you this is because, when I was a student, I always wanted to practice to get up to speed for exams. And sometimes I was looking for practice problems. And anytime I could make up my own, I found that to be a real big advantage, right? So if you have MATLAB, you can check your own work with doing any kind of unit conversion. Like make up problems, do it by hand, check your work in MATLAB. All right, so here we go. What we know here is that we were given a unit problem. So the first thing we do here is, and you don't need to know the exact details of why, but we want to do assign this variable u where we can do unit conversions. Okay, so accept that part on faith. That's just part of the programming environment. Okay, so from there, I'm going to type in row. All right, row is the thing we're trying to convert. And what I know is that it was 0.025. And then I use the multiplication operator, okay, times u dot pound mass. Okay, so the abbreviation for pound mass is LBM. And you notice it's giving you hints. So you can use that hint. All right. And then we divide by units. So it's still need the U. The dot operator, you're going to find if you do some programming, the dot operator is important for classes and structures and that kind of stuff. But just take it on faith right now. Inch. Okay. And then we're going to cube that. All right. So that defines this. And I can run it. And it tells me, here's the thing with symbolic. It's trying to always force this into exact precision math, right? So it makes this into a ratio. Okay. Before we move forward, I want to show you how to take that same variable, right, and convert it into a decimal number. So VPA stands for Variable Precision Arithmetic. And it's just a way of making MATLAB report back things that aren't fractions. Okay, so the variable we're working with is row. So I hit that, hit run, and you see it's 0.025 pound mass per inch cubed. All right. So hopefully, it's a lot of typing, but really it's pretty straightforward to do. You get fast at figuring out how to enter that. Okay. So the next thing I want to do is I want to redo this. All right. I'm going to do the unit conversion. I'm going to call it row again. It's just going to write right over the top. And it's unit convert. Okay. Row, the thing we're trying to convert. And then we put in the units that we want. U dot kilogram divided by U dot M for meter cubed, right? And when I hit run, it should make that conversion for me. And it does, and it shows the irritating, fractions that are harder to interpret. Okay, so I can again do DPA row, and if I do that, watch what happens. I get a ridiculous number of decimal places. Okay, and so I can control that and say, well, I want to only see 3 significant digits. Okay, and there we are, 292.0 kilograms per meter cubed. All right, so you might be thinking, well, Dr. Thompson, your answer was 693 kilograms per meter cubed. What's the difference? Well, remember, I didn't use the exact conversion factor per pound mass to kilograms, whereas MATLAB is using a lot more precision with that answer. So 292.0 is actually more correct than 293, right? Hopefully that makes sense. Okay, the next thing I want to show you is sometimes this looks intimidating, but I could have just, instead of doing this in 2 steps, I could have just said BPA and then unit convert and then row and then the conversion. All right, and then I want 3 decimal places. All right, put it all into one thing and I get the same answer. Okay, so I just wanted to show you that you can string all these things together. It's a little harder to read that way, but you get pretty fast at doing that. Okay, so there's a little bit of start on MATLAB and unit conversions, and I'm hoping this helps you keep things straight. You notice how precise I had to be to make this work out in MATLAB. It forces you to have some mental discipline on how you're doing units. So I felt like it's worth it to bring this into the course. All right, so we'll do a few more examples with another video.